coal is bad for everybody, and some countries have no option if they want to keep growing economically, like China and India. But even rich countries are playing subtle games. If US is exporting coal, then is it really free of guilt? Well, everybody is sinning, but that's no excuse not to phase out coal. So, just like smoking, even though we know smoking is bad for us, we may not be able to just give it up. And here, if economic growth is very important and energy is an absolute must for growing economies, then you obviously ignore the fact that coal is deadly toxic and not at all good for anybody. So it's obviously good to have some way of thinking about phasing out coal that may be feasible socially and politically and economically as well. In the US, coal is becoming more and more uneconomic to dig out of the ground and sell it, but it'll go on even with some subsidies, because coal miners can be a voting base. And a state of West Virginia, where one of the senators comes from, is dead set against many things unless he can protect his base, right? So this is a paper that does some integrated assessment modeling to chart out some socio-political feasibility of coal power phase out and its role in mitigation pathways. Okay, so obviously the best option is if coal just becomes so uneconomical. Why is it jumping? Uneconomical that we can leave it in the ground. These, oil, gas, coal, they are money freely available in the ground. If it's in your neighborhood and you have full control over it, you'll want to dig it up and use it or sell it, right? So what's the introduction, the abstract here? In IPCC pathways limiting warming to 1.5 degrees C, global coal power generation declines rapidly due to its emissions intensity and substitutability. However, we find that in countries heavily dependent on coal, China, India, and South Africa as the top three. But as I said, those who are producing and exporting, like Australia, for example, are a part of this blame game as well. So this translates to a national decline, twice as rapid as that achieved historically for any power technology in any country. That's how fast we have to go down. This is relative to the system size. So you have to look at the economy and how the transition happened in power technology and what needs to happen now with respect to the economies of China, India, and South Africa. This raises questions about socio-political feasibility. Here we constrain an integrated assessment model to the powering past coal alliances. So that's powering past coal alliance. Okay, so you can understand what their goal is. So their differentiated phase out timelines of 2030 in Organization for Economic Cooperation and Development, European Union, so OECD, European Union, they want to phase out coal, and they have this powering past coal alliance, and they have a plan. And 2050 elsewhere, so 2030 is for OECD and European Union, but others have 2050 as a goal, which for a large coal consumer lies within the range of historical transitions. So 2030 is right here, right? We are in 2024 September. So before you blink it, you will reach 2030 in terms of how infrastructure transitions, building new grid, new power capacity, power generation capacity, etc. go on. And 2050 is not that far either in terms of the range of historical transitions. We find that limiting warming to 1.5 degrees C then requires CO2 emissions reductions in the global north to be 50% more rapid than if this socio-political reality is ignored. Okay, so obviously global north has to move much faster. This additional mitigation is focused on Europe and the United States in transport and industry and implies more rapid decline in global oil and gas production. So let me read again to make sure we understand what we are seeing. We find that limiting warming to 1.5 degrees C requires CO2 emissions reductions in the global north to be 50% more rapid than if this socio-political reality is ignored. If you don't phase out coal, then you have to do something else to stay within 1.5 degrees C, which means global north has to go 50% more gangbusters on mitigation. Wow. All of this is pie in the sky anyway, considering that we are still ramping up CO2 emissions and even accelerating them, and we may be close to reaching peak emissions but not there quite yet. So these are some details that I won't go into great details. These are figures analysis that I won't go into great details here because we'll just read the discussion. But basically this is showing 10-year percentage point decline in generation share. So this is the total generation in gigawatt hours, and these are all the countries that you see here. This is the average, and the United States is up here, and this is for coal, oil, gas, nuclear, and hydro. You can see some are ramping up. Hydro is ramping up in terms of total generation. So this is 10-year percentage point decline in generation. And you can read the numbers. Countries fastest 10-year declines in technology's generation share, 1960 to 2018 for OECD countries, and 1971 to 2017-18 for non-OECD countries. So different periods are used. For each country, the fastest percentage point reduction in fuel's share of power generation over any 10-year period is plotted against that country's total generation at the start of that period. So, those kinds of details, but the main thing to note is that the numbers are negative here. So if you don't decline, then you are here. So world record decline is of course this line. So Korea over 77 to 87 had 80% decline, and United States here over 08 to 18 has only about 25% decline in coal. So it's not just China and India, but you can see that since these are negative, you can see India or 78 to 88 hydro minus 20%, and is there a coal number? So obviously you get the idea that they are tracking how countries are doing. Let's just read the rest of it. The dashed line represents the least square's best fit and may be interpreted as an average pace of all countries' fastest transition relative to the size of their generation systems. The solid line is the closest to the x-axis that contains all the points and represents the world record of the fastest transitions by the fastest countries. Note that these lines are included to illustrate the range of the dataset rather than to hypothesize a particular relationship. So that's not a regression line, it's just to show what we are observing in data. While most historic transitions have been driven by technical and economic factors more than deliberate policy, two well-known policy-driven transitions are also plotted for illustration, marked with crosses. So you have now you have to go and find the crosses. That's not going to be easy. The United Kingdom's climate motivated coal phase out in recent years, and Japan's post-Fukushima nuclear phase out. Neither was that country's fastest transition. So what does it mean? UK is making great plans to go net zero, and their carbon energy intensity of the GDP and carbon intensity of the power generation is going down. But it's a small country and it's doing well, but there are lots of feedbacks now in terms of riots, conservative government losing, and we don't know what will happen with the liberal government in terms of dealing with all the issues and so on. So here is the United Kingdom and here is Japan. So United Kingdom made specific plans to try to phase out coal, so it's here at minus 30% in terms of the gigawatt hours. So you have to read these carefully because here gigawatt hours are increasing and these are decreasing, declines. And Japan, after Fukushima, tsunami happened, Fukushima got damaged, a lot of people died. They got completely spooked. It's a small country with very little land and very few resources. So they decided that nuclear was just too dangerous. So they started saying we need to use coal to be safe. But actually, if you look at the data, even before Fukushima, there were some adjustments happening. So nonetheless, gives you a sense of how these transitions work. So there are more details here, energy system implications of PPCA constraint and so on. So those are the scenarios that I won't go into. Okay, so let's just skip this. This is showing various pathways from 2020 to 2050 and 2020 to 2100 in terms of percentages here for 2050 and percentages for 2100 for again the various things like coal, default coal, gas, default gas. So just to make sure we are not missing anything, let me open the file on the side. Sorry, I do this because oops, I'm having some issues with my I don't want to be in this directory. I want to be here, I want to be here, I want to be here, and I want to be here. So let's look at the text while I talk so that I see if I will miss any important point. Did I? So I already missed figure 1. Yeah, I skipped this one. So that's why it's important to look at this. Let me, yeah. So sorry to do it this way. You have to be better prepared, but it doesn't matter. So decline in fossil fuel usage from 2020 to 2030 in IPCC 1.5 degrees C, low overshoot pathways, and in one of the integrated assessment models. And this is talking about how staying within 1.5 degrees C by 2100 with 67% probability will require that we phase out coal and make other transitions. So here we have coal, oil and gas, and we have the scale here in terms of maximum third quartiles. This is a standard whisker plots, box and whisker plot, which shows various things. But obviously in terms of percentage change in generation and change in primary energy, where your primary source of energy is from, coal has to drop greatly by 2030 if you want to stay on the path to 1.5 degrees C, and oil has to drop, even gas, the so-called low emission fossil fuel, has to drop. And this is the percentage change, and you can see the percentage change of gas has a large range, but coal has to drop by 70 to 80%. Okay, so PPCA is another IAM model. So let's skip those kinds of details. Sorry about skipping this, but you got the point here on where everybody wants to go. So this is coal power decline 2020 to 2030 under climate constraints compared with historical power transitions. So how things have happened in the past and what we need to do to stay on climate targets. So there is the US again, Japan, Germany, Korea, and that's the world record you would want to have. South Africa, India and China are over here away from this. So obviously they still have lots of power generation that depends on coal, that has to decline by a lot. India is going to burn coal for many more years, with majority of its power likely coming from coal. So this is the total generation. This is for 10-year percentage point decline in generation share. This is the percentage point decline in generation share. So here this is assuming linear decline either from 2020 to 2030 or from 2030 to 2050. That's for OECD 2030. Sorry, this is again just indicative lines. 2020 to 2030 is for OECD and EU, and 2030 to 2050 is for other countries like India, China, and so on. So this is energy system implications of PPCA constraint. Let's make sure we understand what we mean by that. You are getting the point that these are scenarios which tell you how you can actually do this transition phase, coal phase out, to be acceptable socially and politically. So obviously I'm saying words here as we scan through the text for some of the points. So TIM. So PPCA here is powering past coal alliance. Okay, powering past coal. That's the goal of this alliance. So just depends on how you read it, right? So here is another figure showing CO2 emissions with and without PPCA constraint, powering past coal alliance constraint on the 1.5 degrees C. So again, that's OECD EU target, and they want to really do this. But if you watch the Ukraine-Russia conflict, then Europe was doing a fancy dance on how to get past winter. They were willing to fire up coal plants. They bought more gas from Norway and US, and they said gas is a low emission fossil fuel. That's not a good thing if you're trying to claim a lot of progress on renewable energy. So it's a wake-up call in terms of just how low we are on renewable energy share, that a little perturbation will make us running helter-skelter. So even though it sounds very good when we say we are getting a lot of the energy share from renewables, primary share is growing in renewables, and a little perturbation like Putin turning off the gas spigot makes us panic, then obviously we have not become quite resilient against coal and fossil fuels, right? So sorry about this helter-skelter reading, but the main message here is that this study reinforces the importance of rapidly phasing out coal power generation, but observes that the challenge of coal phase out is unevenly distributed. We make this judgment on the basis of the size and diversity of countries' power systems, like China and India, South Africa being good examples. Economically growing countries with very diverse power system, and they cannot easily phase out coal. Often I always say, because Western countries also put sanctions, let's say on Iran or Russia, and then India cannot buy oil from here, cannot buy oil from there, and they cannot burn coal. So how is it going to grow economically? So socio-political considerations are very important. Okay, while efforts to reflect social or political values in models are in their infancy, the very purpose of the global energy system modeling in informing policy may be under challenge if some solutions, including economically optimal ones, are not socio-politically feasible. Okay, so models deploy multiple mitigation options, and less mitigation in one area can be balanced by more mitigation in another, while achieving the same overall emissions or temperature goals. So models are good for playing these sensitivity analysis or scenario pathways, but one reason that feasibility questions arise in optimization modeling is because a pure unconstrained optimization model would tend to near instantaneously near instantaneously switch the system to whichever options are the cheapest, which means burning as much coal as possible, right? However, the application of too many constraints can lead to the modeler effectively steering the model towards their prejudged realistic pathway, which again will slow down the phasing out of coal, for example. Okay. Expanding comparative feasibility analysis beyond coal power phase-out suggests a fruitful area of future research to reveal the implicit rates of growth and decline arising from models alongside explicit user constraints. This would allow model users to see which judgments have been made and to accept or challenge them. It could also enhance policymakers' ability to interpret and understand models. In the example raised in this study, energy system models have rightly highlighted the relative advantages of coal phase-out in mitigation, but relied on it to an extent that raises socio-political feasibility concerns in the countries where coal use is concentrated, India, China, South Africa being the top ones. Rebalancing mitigation measures could show more feasible paths to achieving the Paris Agreement goals. So there are issues of whether 1.5 degrees C is really a scientific target and so on, which I have talked about elsewhere. But leaving all that aside, coal is bad for health, and we need to phase it out, but we also need to provide realistic pathways for economically developing countries to better the lives of their people. So this is important work. At least this research is important in putting social political feasibilities on the table for preaching about coal phase out. Nobody is really doing it. Even the best net zero pledges from Sweden and Denmark and so on do not phase out their coal power plants till the 1940s. Nobody is brave enough to just shut down coal power plants yet. Okay, so with all those realities, just keep in mind the message that social political feasibility pathways are critical for phasing out coal, especially for economically developing countries like India, China and South Africa and the rest of them. Okay.